Hello everybody, my name is Ronit Banerjee and this is my ZID, Z5590815, and we'll be going through the fundamental laws of planetary motion, and I'll be sharing my insights that I gained throughout the experiment. So let's begin. So starting off with Kepler's three laws, his first law, which is the law of ellipses, states that a planet orbits the sun in a path shaped like an ellipse, not a perfect circle. In this ellipse, the sun is located at one of the two focal points rather than the center. This means that during its orbit, a planet's distance from the sun changes. It can be closer at some times and farther away at others. Kepler's second law, which is the law of equal area, states that as a planet moves around the sun, it sweeps out equal areas in equal amounts of time. This tells us that a planet travels faster when it is closer to the sun and slower when it is further away. Even though the speed changes, the area covered in a set amount of time stays consistent. Kepler's third law, which is the law of harmony, states that a time a planet takes to complete one full orbit is related to how far away it is from the sun. Specifically in the equation, which is the square of the orbital period, is proportional to the cube of the semi-major axis of its orbit, which means the farther a planet is from the sun, the longer it takes for it to orbit. So let's dive into the experiment questions now, starting with question number 9a. So 9a actually asks us, does the planet move as the moon orbits around it? The answer is yes, it does, because the moon's gravitational force affects the Earth much more significantly than the Earth's gravitational effect on the sun. This is mainly because the moon's mass is a larger percentage of the Earth's mass compared to the Earth's mass relative to the sun. Additionally, the moon is much closer to the Earth than the Earth is to the sun, which increases the strength of its gravitational influence. Question number 9b actually asks us to qualitatively describe the center of masses in question number 1, 4, and 7. So we see that the sun-planet system, the center of mass lies well within the sun due to its overwhelming mass compared to the planet. Even if the planet's mass were doubled, as proposed in question number 4, the center of mass would shift slightly closer to the planet, though the change would be minimal. Likewise, a reduction in the sun's mass to 3/4 of its original value would also move the center of mass towards the planet. However, the shift would still be relatively small and largely imperceptible. 9c actually asks us to compare the Sun, Earth, and Earth-Moon scenarios. So they both actually orbit their shared barycenter, but they're vastly different mass ratios, with Sun-Earth being 333,000 to 1 and Earth-Moon being 81 to 1, put those balance points in very different places. In the Sun-Earth system, the barycenter sits just 450 kilometers from the Sun's core. Deep inside is a 695,700 kilometer radius, so the Sun's wobble is essentially invisible. In the Earth-Moon system, the barycenter lies about 4,670 kilometers from the Earth's center, just beneath its 6,371 kilometer surface, so Earth visibly swings by thousands of kilometers each month. Consequently, Earth behaves as if it orbits the Sun's geometric center, whereas the Moon truly circles a point just under Earth's surface. So moving on to question number 11, we are asked, what is the distance between each marking in AU when the grid lines are turned on? So if you can see in this image over here, between the two grid lines, given that the star is the Sun and the planet is the Earth, it's 1 AU long. Therefore, each grid line would be 0.5 AU. Question number 14 actually asks us to record the time it takes for a planet at 4 different orbital distances to complete one orbit. So as you can see in the table, I've used the distances 0.5, 0.75, 1, and 1.5. And if you notice, the orbital period actually increases proportionally to the orbital distance. And you can also see that in the screenshots below. So does this follow Kepler's third law? Yes, it does, because you square each orbital period and divide by the cube of its distance from the sun, you get essentially the same constant every time, as you can see in the examples below. Because p squared over a cube remains constant, the data follows the relation of p being proportional to a to the power of 3 over 2, which is predicted by Kepler's third law. So question number 15a asks us, which planet in our solar system do you expect to have the fastest orbital velocity? The answer is Mercury. At just 0.39 AU away from the Sun, Mercury travels at around 47.9 kilometers per second, which is the quickest of any planet. Question number 15b asks, which planet do you expect to have the slowest orbital velocity? The answer is Neptune, orbiting at roughly 30 AU. Neptune only travels at about 5.4 kilometers per second, which is the slowest in our solar system. Why is this? This is because the planet which is closer to the Sun, the gravity is much stronger, so a planet must race along its path to avoid falling inward into the Sun. The farther out the planet is, the Sun pulls weaken, letting distant planets drift more slowly. Question number 16. What did I learn from this experiment? So simulating these orbits gave me a deeper grasp of planetary motion and Kepler's laws. Watching each planet trace its ellipse, sweep out equal areas, and then confirming that squaring its period and dividing by the cube of its radius yields a constant made the theories come alive. Crunching and plotting these results showed gravity and motion perfectly balanced, cementing how these elegant laws govern our solar system. Thank you so much for listening, and you'll see the resources on the next slide, and I'll also be posting the slides in the description as well.